physics, we came already in the domain of physics and materials in Berlin. He stayed with us for 4 years. He was my friend for me and to discuss in the details of transmission electron microscopy, spectroscopy, and use a lot of techniques associated and has done his own research. At the present time, since he left us, he is in the Fritz Haber Institute of Max Planck Society in Berlin, where he has a large group of people doing materials and electron microscopy. He will talk about that. At the present time, besides this subject of graphene, Marc is highly engaged in catalysts for water splitting and other needs of copper oxide and other materials. But his main mission there is the electron microscopy to the state of the art. So please, let's welcome Marc for him.
Thank you very much. First, I want to thank the organizers for having me here. It's a pleasure. You know, I like the support very much. And today I'm going to speak, the title is a bit long, so I'm going to speak about the dynamics that we observe when we look at these materials in the microscope under reactive conditions. What we're doing in Berlin is we're trying to understand how catalysts actually function. And when we do TEM, you know, in the microscope, you have these electrons which are extremely strongly interacting particles. And normally the electron beam flies through vacuum, interacts with your sample, and you take pictures. But we want to do more than just taking pictures of particles that are in vacuum. We want to do chemical electron microscopy. That means that we don't just look at atomic arrangement, but we also want to learn something about the chemistry. And now, I needed to show some atomic resolution pictures. I'll probably talk about scanning electron microscopy, but with electron microscopy, we show something. So, with these new microscopes at the moment, you can resolve something in the range like 50 to 70 picometers. So the resolution is good enough to see an atom, and there's nothing, there's another atom. So the resolution is high enough to basically solve most of the problems. And you can then actually do even spectroscopy on a single atomic level and understand the materials, you get spectral information. And with different detectors, you can study very complex materials. This is just a mixed metal oxide material. And what I just want to show you here is an example of how we get chemical information is because of these microscopes, they are such a high spatial resolution and such an accuracy in scanning that you can record in this complex mixed metal oxide not only intensity information to say which kinds of atoms are sitting there, but you can actually feel, I don't know if you see it in the back, probably not, but you can see the cations and you can actually, and zoom in a bit, you can actually even see the oxygen atoms surrounding the cations, and you can, for example, measure the position of the oxygen atoms around the cations and measure the octahedral distortion, get information about the oxidation state of the central cation. So what I want to say is with these modern instruments, we can, like Feynman suggested, build a machine, look where the atoms are, and then you understand how this thing works. And with these microscopes, we can do the same. But the problem is, as I said, the electrons are strongly interacting, and you need vacuum, so the materials is in vacuum. And we are studying catalysis, and a catalyst is not in vacuum, it's interacting at some temperature with some gas phase. So for chemical electron microscope, it's important to also take in the chemistry in some ways. So what we try to do is we try to look at the chemical dynamics and how the material then behaves. And there are some early studies about the reaction of a material with a certain gas phase. So this is a famous publication from the beginning of environmental TEM. It shows a copper catalyst on a zinc oxide support under different atmospheres. And what they have done is just exposed the particle to a certain atmosphere in the microscope and waited for 1 hour to take atomic resolution picture of an equilibrated state. So this is actually a surface-optimized shape of the sample that it adapts shape to the chemical potential of the gas phase. And what you see here is again a static state. It's not changing, it's not dynamic, it's a thermodynamical equilibrium, it's not an active catalyst. So what we actually want to do, we want to study a catalyst that is dynamic. And this is not a good picture, for example, for a real catalyst because it changes once and then it's over. But a real catalyst is something that goes back and forth. It has to react several times. The catalyst shouldn't deactivate immediately. So it does a reaction, comes back, it does a reaction again, like a pendulum. You have your gas phase that is pulling in one direction, the catalyst is helping to do something else. And there are indeed some reactions where we could, Professor Erdmann got a Nobel Prize for imaging these chemical oscillations. So what I have shown in the previous slide here this is not so relevant for catalysis because it just shows how a system adapts to a certain surrounding and then stays there. But we want to study dynamics. And that is the challenge. So we want to see our material under relevant conditions for catalysis. And that means in catalysis you can see lots of dynamics, but only a few of them are really relevant. So in order to be sure that we're looking at dynamics that are relevant for catalysis, we should actually be able to detect the product. And as you can imagine, in the TEM, we very small amounts of sample, and the products that we create are also just in very small amounts. So the detection is quite difficult. And then in the microscope, you need to make sure that you know the atmosphere, which is also not easy because the microscope is not a good reactor. And of course, you must make sure that only your particles are active and not any other materials that you use in the microscope. I showed just one example. This is a nice example because you can see the active catalyst and you can see that it's doing the product. So you know it's active because you see the product. The product is not a gas phase that you need to detect somehow. You can just directly see the carbon structure that is forming. Recently, people have shown that they can look at the catalyst particles in the reaction and at the same time detect protons. This is a platinum particle in the process of doing CO oxidation. As you can see here and also here, as soon as a catalyst is active in doing things, you can forget about real atomic resolution pictures because most reactions are actually so fast on atomic scale. No matter how many millions you spend on an electron microscope, the dynamics make it nearly impossible to get atomic resolution images. You see the speed of the movement of that is just fast. So we follow different approaches in Berlin. We don't have an environmental TM, but we have some commercial holders that actually allow you to introduce a nano laboratory into the TM. I will not speak about this today because we just started with that. Then we have some microreactors where we actually do chemical reactions on TM grids, but not in the microscope. We do it ex situ, but at least we know the conditions that each particle sees. And then we can go to the microscope, study the particle, go to the reactor, and back and forth. I will also speak about that. I will speak about in-situ scanning electron microscopy today. So this was my introduction. So this is the microscope that we use. It's a conventional scanning electron microscope that you can buy. We just slightly modified it. So we have different gas flow meters to choose our atmosphere that we're interested in. We have, it's not shown here, we have in the back a mass spectrometer to analyze the gas phase. And we have slightly modified the heating stage. So we use now a laser fiber and we attract infrared light just below the sample, so we can heat up the sample and make sure that just the sample gets hot. And we use this microscope, amongst other things, to study the growth of graphene. So graphene is a very hot topic, there's lots of money in research of graphene. And because the growth happens at a very high temperature, for example at copper you go at 1000 degrees, and what is growing is just a single atomic layer of carbon. It's difficult to understand actually how it grows. So people have figured out lots of complicated experiments. Actually this is from 2013. A group, they used carbon isotopes. So they were feeding hydrocarbon into the chamber and they were switching between C12 and C13 isotopes. And after growth, they took out the sample and studied this Raman, how the growth forms were propagating. They got different shapes and then we explained how the growth happens. So we actually started to look at different systems. First I will show a bit about how graphene grows in nickel and copper, then platinum. The whole story started with a group from Cambridge. They came to Berlin. There's a synchrotron, and we have there some high-pressure XPS machine. And this group was studying nickel catalysts, and they did chemical vapor deposition growth of graphene. And while they were doing that, they were looking at the carbon 1s edge with a synchrotron, this XPS machine. And they watched this as a time axis. They started dosing the hydrocarbon. They looked at the carbon K edge region. And this time, so first there's no carbon on the surface, but then it's the evolution of some features. Different positions with time, and they thought at first at the beginning we have adsorbed carbon species, the hydrocarbon dissociates, and the carbon goes into the nickel. It's the same with nickel. Nickel has a very high solubility of carbon, so lots of carbon can go into the light. And then with time it comes to the surface, you see a peak shift again, and they have the graphene. But this is just a spectrum, so they just from the spectral energies they thought how it should happen. And that was the ramp that they were driving, so they were heating up a sputtered film to make the first polycrystalline, and then they did isothermal deposition, or CVD process, and then they were cooling down. And so they asked us if we could do the same thing with the scanning electron microscope. So the first thing is the looping medium. This is a sputtered film, we heat it up and you see the development of grains. It's just a 300 nanometer thick sputtered nickel, heat up, uniform grains. then we started at the same temperature to dose ethylene and hydrogen. And then you see some dark contrast due to the precipitation or deposition of carbon. And I would say this is for sure graphene, but it's carbon deposits on the surface. And it's interesting, you see sometimes the contrast is not homogeneous, it's like flickering. And then I already mentioned that nickel can take up a lot of carbon into the bike. When you then cool down, it was the next thing we did. You see actually the precipitation of a lot of carbon back to the surface. And this shows you why it's very difficult to grow really thin layer graphene on nickel, because depending on how much hydrocarbon you dose, how much carbon goes into the nickel and how fast you cool down, you can have a lot of carbon just precipitating to the surface. So we made a closer look on this process. So this is a movie recorded at 600 degrees around. We use ethylene and hydrogen as a precursor. And you see again there's a carbon deposits forming on the surface. We did some analysis, it's not single layer graphene in this case. And in some grains it stays confined to the grain, in some other places it just spreads around. And then we changed the atmosphere to see what happens. So when we switched off the hydrogen, funny thing happens, it seems that the carbon starts to disappear. It's still flickering a bit, but in most places it just disappears. I just zoom in here, you can see it in more detail. There's still carbon forming, but it somehow seems to disappear. And when you switch off the hydrogen. The funny thing is when we turn off the hydrocarbon and introduce the hydrogen back into the chamber, it takes a while until the atmosphere really exchanges. But once the hydrocarbon is out and just hydrogen is in the chamber, it seems to reprecipitate the carbon back from the volume to the surface. See, as everything is getting dark again. So there are different ways to explain it. One possibility would be that the hydrogen has an even higher solubility in the nickel and forces the carbon to go back to the surface. So we switch back and forth and just skip it, but you can get the carbon back in and you can get the carbon back out. It's a nice game. It's actually relevant not for graphene growth, but maybe for people who do catalysis and don't want that they have a catalyst coated by carbon. So we looked a bit at these dynamics, and I just wanted to show this because the nickel is really not a good system to grow a nice, beautiful graphene because of this high solubility in the bulk. So we switched over to copper. Copper is different because copper has basically no solubility for carbon. In the case of copper, the CVD growth of graphene is really a surface process. And now I advertise a bit the techniques, and in this essay we can do basically the whole thing. We can make the sample side, anneal it, roll it, and cool down. Let me show you this in a sequence. First, the motivation was because we want to understand what is happening and how this graphene grows. And we check the literature, and of course people are trying to model how the graphene grows on copper. So some DFT people, they assume perfect surfaces, like a 111 terminated surface, and 100, and so on. And they do DFT calculations to think of how the graphene actually ascends. And people studied samples after graphene grows and try to correlate how the graphene grows in different facets of the copper. And actually the literature has lots of different conflicting findings. So we did everything in the microscope. As I said, we started with annealing first. And just the annealing alone is interesting because we got lots of samples also from Cambridge, for example, and they had lots of contaminations on the surface, silica particles as we found out. And they assumed because they do the annealing process in a quartz furnace that some of the silica comes from the furnace. So we did that. This is a rolled foil as we buy it. And we did the annealing process just to see what happens. And we also knew from other publications, many people, this is from the literature, you see here this is graphene, the darker things here, and you have lots of white particles. We knew it's a common problem, so let's see what happens during annealing. And in our microscope, it's not a silica furnace, it's just like not a quartz furnace, it's just a SN with a one. So let's see where the silica particles come from. And this is now a video that I start. This is our setup. In the beginning, we didn't have the laser heating, so there's a normal crucible. This is our copper foil. We spot well the thermocouples to directly measure the temperature of the foil. This is our gas inlet. And now we're zooming in. You see some stripes from the rolling process of the foil. And as the temperature increases, you see some grain boundaries, but above like 500 degrees, these grain boundaries start to get moved. And you see that these grain boundaries move around. And we're nearing hydrogen at a certain temperature. At this condition, you get some surface roughening. When you heat even higher, like 900 degrees, suddenly lots of white particles are visible. And you see there's like a kind of a grounding motion of these white particles on the surface. They go in different directions, bounce around, and you have the impression that the surface is a bit melted. And that's actually the conditions at which you grow graphene, 900 to 1000 degrees. So I went to the literature, and it's actually known since a long time that before a metal reaches a bulk melting point, melting starts at the surface. It's called surface pre-melting. And in some papers you can see that the surface pre-melting, this is actually temperature in kelvins, starts really far below the bulk melting point. And because the structure is different for different orientations, like the 111 is a closed-back structure, the pre-melting starts later than on some open structure. In this case, it's clear that these DFT simulations that start from rigid, terminated copper are questionable because it's much more dynamic during growth. So that was the annealing. Now let's have a look at how the graphene grows. So after annealing, we just switch from hydrogen to hydrocarbon hydrogen feed until the CVD grows. What you see here, this is looping, I found several times. What you see here is polycrystalline copper foil, and you see that at some places here, graphene flakes are nucleating. The surface is still mobile. You see the grain boundary is shifting to the right, for example, here. White particles are still there, they're moving on the surface. And I just want to point out the thing is, this thing is at 1000 degrees. It's like as bright as a light bulb inside the microscope. And we're looking at the secondary electron detector in the SCM, and we see the formation of, in this case, it's really single atomic layers of carbon. So it's giant. At the beginning, I didn't believe that we would be able to see that, but the graphene offers such a good contrast in the secondary electron microscope that you can actually see it. And in addition, there's another thing. When we work at high temperature, you don't have any problems with contamination in the SCM. So we have this movie, and then it's of course easy to analyze the growth speed. We analyze the nucleation behavior, so we see clearly it starts to grow after you have supersaturation of carbon species on the surface. And by looking at the nucleation rate as a function of time and the growth speed and so on, we can basically get so much information out. And it's much easier than to do the switching experiments or to grow and run to a microscope and grow different conditions, run to a microscope. And we don't miss anything. For example, during cooling, there are lots of things happening that are quite interesting. At high temperature, you don't see anything. It's like a surface pre-melted surface of copper. But when we cool down, suddenly, at the beginning, you don't see any features on the surface. But during cooling, suddenly, steps evolve. And actually, these steps are forming at relatively low temperature. Copper, you would think it's solidified very early, but these steps are forming at the temperature of around 700 degrees. You see it here, this is the temperature, this is the aspect of the surface, this is a graphene island on the copper, and during cooling you see that it starts to form steps and facets. We have these hills also, here it looks like a hill-shaped surface, because at 1000 degrees the copper has a lot of sublimation, so we lose a lot of copper. Actually we coat our microscope and the inside we see with copper. That's why we cover everything with aluminum coating. And so when the surface is due to sublimation going down, at places where you have the graphene, it stops the sublimation, and then in the surrounding, the surface goes downwards, and the covered region that is covered with graphene, when it grows like such a hill-like shape. So we have lots of such hills, and during cooling we form these steps. And as I showed before, the surface pre-melting, the surface dynamics are depending on the orientation of the copper grain. When you have a 111 closed-back surface, it's more rigid, and there's not so much surface dynamics and not so much sublimation. And I just zoom in here, this region, 2 steps. See, one region, the surface aspect is different to the one on the other grain. And you can see this one here is a 111 surface, and it's basically growing like relatively flat, not so much sublimation. You get actually hexagonal shaped graphene sheets. In other regions, different orientation of the copper, you have much more mobility, much more sublimation, and you have more exposed formation of these hill valley structures. And it was a bit interesting because we have a mass spectrometer connected to our growth chamber. Lots of people in the literature grow and they use simple vacuum pumps and KF flanges, and no one monitors really the atmosphere. They purge its argon and they go to growth conditions. But we have the mass spectrometer and we see that we have small amounts of oxygen in the chamber. It's not a huge machine, so there's always some oxygen. So we looked at the copper phase diagram, and I know that we are working in this regime. This is oxygen partial pressure, and we are somewhere here. At growth temperatures, that's up here, we see copper. But when we cool down, at one point we run into the scenario where the copper oxide is actually stable under these partial pressures of oxygen. So we had a look, we cut our sample after growth, so this is some carbon species on the surface, it should be graphene layer, it's very beautiful here. And in the TM cross section, we can see that there's a like 5 nanometer thick, depends from place to place, regime of copper oxide, clearly identifiable. So actually, meanwhile, it's known that the oxygen plays a role in graphene growth, but we are still interested, what does the oxygen actually do? How does it contribute to the CVD process of graphene growth? My boss is an expert in catalysis, which I'm not really, I'm a physicist, and he told me right from the beginning, it's just copper metal alone, you would not dissociate hydrocarbon unless it's thermal decomposition, but we know it's not thermal decomposition. So he already postulated oxygen plays a role, and he was right. But we wanted to study more the role of oxygen on copper at these temperatures. So we started systematic oxidation processes in the ICM. I just show a few things now. This is, for example, how it looks like when you oxidize copper at around 600 degrees. So copper foil, and then islands of the CO2O are forming. It's quite beautiful how you can visualize this. And in a microscope, it's wonderful. You can just change the partial pressure of oxygen, change the temperature, and we can study that under various conditions in complete phase diagram. The next step is once you have the copper oxide, so the first one that forms the CO2O, we can further oxidize to a higher oxidation state, to CuO. And you see that when the CuO forms, there is actually an interlayer first spreading out before you see the CuO. And that's very interesting for catalysis. So we do some catalytic reaction where copper is a catalyst, like ethylene oxidation, for example. And it's known that there are different copper oxidation states, but the people so far do only spectroscopy. They see different oxidation states, but they didn't know how actually the surface looks like during such, when they're exposed to such conditions. Here just is colorized, and you can see better this interfacial layer that forms between the different oxidation states of the copper. And even more interesting it gets when you actually, from a boring oxidation, go to something that actually could involve some chemical reaction. So we look at the surface, how it looks like when you have mostly hydrogen, and you just add a little bit of oxygen. So it's not yet dangerous, no explosions happening and so on. But this is the redox dynamics of copper, as you see in the SCM. And what you see copper, and in between there are ions forming, but the CO2O. And now we see that, and then it goes back and forth all the time. This continues for hours and hours and hours and hours. And it's interesting, it's an oscillating reaction. So you have places where you have the copper, then you have again the copper oxide and the copper. And the reason is you have hydrogen and oxygen in the chamber, but there are different splitting probabilities for oxygen, for example, on copper and on copper oxide. And actually it doesn't need much, but it starts to oscillate. It's very beautiful. So we are trying not to study this as contact temperature, oxygen partial pressure. And the good thing is, when you just do in-situ spectroscopy, you have the conditions and you record spectra. You see different copper species, but you wouldn't see the dynamics. But we can now do these experiments under exactly the same conditions as the spectroscopists, and we deliver the visual information. So then we can tell you, look, it's not just one strange copper phase, it's actually phase separated into different types of copper. So that's just to show you a bit of the dynamics of copper. So now we switch to a new catalyst, platinum. Platinum is very good for graphene growth, as we have figured out. We'll just go quickly to some of the results of the platinum. Again, first we anneal at 1000 degrees. You can see it's just also beautiful. That's why I wanted to show you. You can see all these dynamics of grain growth, of normal grain growth, some high energy grains disappearing, taken up by low energy grains. Also beautiful in the scanning electron microscope. You have these nice contrast differences due to electron channeling and also work function contributions. So after cleaning the surface of the platinum, we switch to growth conditions. Again, CVD growth hydrocarbon and hydrogen mix it together, and you see that there is some nucleation of graphene. It follows actually the typical 2D film growth. You have lots of islands. These islands merge together, and then you form multi-layers of graphene. This one layer, this is a second layer, and 1, 2, 3 layers, and so on. It's really beautiful because we can, just from the contrast, count actually the numbers of layers that we have. And we see, for example, when different gray graphene domains merge, like here somewhere, when you merge at a specific angle, you can cause a screw dislocation and you form multi-layer graphene. And you see that there are different types of stacking of the individual graphene layers. Meanwhile, we have found out how we can actually grow graphene without any multi-layer graphene. So just single-layer graphene, and we can also do healing processes. So it's quite instructive. And what is very interesting for us, because we're doing heterogeneous catalysis, that's actually the main thing. My boss at the beginning was not happy that we do graphene growth, because he said, who cares about graphene, it's just fashion. In catalysis, graphene is usually not wanted because it blocks your catalyst active surface.
But meanwhile, we see that, for example, here in this video, you see that certain conditions, one grain is extremely active to form graphene. It even can spill over to other grains. And only when we increase the partial pressure, other grains also start to grow. You can see there's even a bit of a growth of that grain and retracts because it's not stable on that grain unless we increase the partial pressure. And then you can study lots of things about growth. And we do electron backscattering diffraction, so we can index the crystallographic orientation of the different grains and study the activity. And that's why it's interesting for catalysis. So we have the different grain orientations, looking at them, how many steps and surface kinks and edges are there, and we correlate this to the catalytic activity. So this is, for example, a polycrystalline platinum foil with all the grains mapped in orientation, and we do the growth experiments. Then we can plot the catalytic activity versus the surface orientation. And so now it was also interesting for my boss time. We can, of course, in the microscope we have monofoil. We can change for different precursors and see how different, different hydrocarbons have different stabilities, and you can see how they are changing the nucleation behavior of the graphene and all this. Just before I conclude, I want to show you one example directly from real catalysis. When we study a very simple reaction, it's just a partial oxidation of methane on platinum catalyst. This is the reactor. They drilled a hole to measure along the catalyst bed the composition of the gas phase. So when you start at position 0, this is actually how it looks like. So the catalyst here is the active place of the platinum catalyst. It's a hole, and you have this probe. You go from here to there and measure at each position the gas composition. So when you start from here, you have the hydrocarbon and the oxygen. And then this thing ignites. And the hydrocarbon gets burned, it starts here, so then the concentration of the hydrocarbon goes down along the bed. Oxygen gets consumed, clearly, we form water, we form hydrogen, and so on. And what I want to point out is when I usually do TM on a catalyst, people do a reaction in a reactor, then you take some powder, I dilute it, I put some particles on my material, but I have no idea if it was here or here in the catalyst. But these particles up here, there's a completely different gas atmosphere than the particles down here. And there's a lot of dynamics, and if you study the whole thing, you don't understand it. So you have to go to a specific point where you know exactly your composition of the gas phase and look at the dynamics. And this we did in case of this platinum catalyst, not in this system. We use again a polycrystalline foil. We were to like 900 degrees with hydrocarbon, hydrogen, oxygen, and we looked at the dynamics. And this is how the surface looks like. It's again a looping movie. Different grains of platinum. Some are coated with graphene, some are partially coated with graphene. Actually, graphene is still growing on some of the grains. And you can see that there is different contrast on the surface. And when I zoom in with higher magnification, you can see that the surface of the platinum behaves very dynamic. So what you have here is 900 degrees. You have a very noble metal like platinum. And I just learned that platinum is noble, wouldn't oxidize at least at 900 degrees in hydrogen atmosphere, wouldn't form a surface oxygen permeated region. But as soon as we just added a little bit of oxygen into the growth feed, we saw these dynamics on some grains. And what you see here is graphene growing on these gray contrast regions, and in the brighter contrast region, graphene is actually edged away. So you see also that the surface is differently reconstructed in different regions here. But basically, it's again platinum that is either oxygen or hydrocarbon, or which is metallic. Like the determination changes, and according to the determination of the platinum, the surface structure changes. So again, 1000 degrees, seeing atomic layers of carbon, and nice dynamics to see in a relatively simple scanning electron microscope. So I just conclude quickly. With SEM, we get detailed information about the growth modes, and you can see the dynamics of surface processes in quite nicely resolved. And the fascinating thing is that you can actually really see single atomic layers of carbon at 1000 degrees. We did post-growth analysis. It's really beautiful graphene. And the take-home message is that when you see the dynamics, you can complement spectroscopic data. There are lots of people fitting lots of peaks with different theories, but in the microscope that we have now, we can actually correlate the dynamics to their spectroscopy data. And that's basically the message I wanted to share. So finally, I want to thank my group members. The group has actually basically doubled in size, and meanwhile I married her. And this is the PhD student who did most of this work on graphene growth. I want to thank you very much.
Questions for Marc?
Well, nice work. Of course, the dynamics you see on the microscope, the dynamics of microscopy are different. That's it.
Yes.
So I would agree that you can now use the microscope to sort filter some theories, but what do you have to say about these different dynamics?
In the microscope, we are always limited with a resolution. We use a scanning microscope, so depending on how much signal noise, how good the quality of the scan should be, we have different scanning rates and different time resolution. But also the acquisition of spectra in XPS, for example, takes several seconds. So now you can play with the thermodynamics of your reaction, slow it down, maybe you change the temperature, or use some species that are not so active, but then you change the whole system again and you add new complexity that you don't understand. It's clear, it is a limitation. But when you compare this with in-situ TM, where you would wish to see the atoms, in in-situ TM, as soon as things get a bit dynamic, you lose everything. And here, because we move further away, we see more statistical information of many, many atoms moving. And so we cover actually here a different time range and different speed of dynamics.
Could you do some kind of spectroscopy, let's say? I mean, just an optical fiber?
Yeah, that's the thing. We have anyhow already an optical fiber inside for heating, so we could then use an optical fiber to ground. We just need to use a laser light that doesn't conflict with the thermal radiation. That's one thing we do. And we have the spectroscopic information about the mass. So we have mass spectroscopy.
Okay. Any other question? Because we still have another presentation. Okay, that's Marc again. Thank you.
Jornadas CICECO 2015. So the next speaker is Susana Olhero. She's from the department, she's a researcher at the Department of Materials and Ceramic Engineering, and she will speak now about microfabrication and ceramics.
So good afternoon for everyone. So first of all, I want to thank the organizing committee for the invitation to be here. It is a pleasure for me to present my work here today. I will talk about high precision microfabrication of ceramic microparts for biomedical applications. So this work is done in the frame of FPCET project called Isabella? Okay. So, as I said, this work is in the frame of the FPCET project called, which acronym is FABINET, Fabrication and Functionalization of Micro Devices for Biomedical Applications. So the outline of my presentation, so I will start talking about the miniaturization, so the trend, the main advantages of miniaturization and the applications of using micro-components. Then I will tell the technologies or the current technologies used for fabrication of ceramic micro-components, the main disadvantages of these technologies and why we need to develop a new technology. Then I will talk a little bit about the new technology the globe has, and then I will show the two demonstrators obtained by this technology. One developed in our lab in the University of Aveiro that are all with ceramic microneedles, and another one developed in collaboration with the University of Birmingham, so pillar arrays for high frequency microtransducers. And finally, the future work. So nowadays the trend is miniaturization of products and parts with feature sizes measured in microns. So why we need to decrease the size of components? So we have several advantages like less material usage, the functionality increases per unit space. We can have accessibility to regions that are forbidden for larger products, and in most cases, smaller products should mean lower prices because we use less amount of material. We have different types of microsystem products used as sensors, for example, actuators or microcomponents. We call microcomponents to all the micro-sized parts that are not sensors or actuators. So the applications of these microcomponents can be applied in different areas, such as automotive components, medical applications, or for chemical and environment applications, or even others. So the common materials usually used for fabricate this kind of components are silicon, polymers, or metals. Now the question could be, why not ceramics? So among several reasons, one could be the shaping technology. So in fact, if you think about the size of these kind of things that are lower than 1 millimeter, it's difficult to find a technology able to produce this kind of micro things at a reasonable price with high final quality without need of machining in the hand of the microcomponent. So we have two current colloidal shaping technologies to obtain this kind of microstructures. One is called VPP, viscous polymer processing, and another one gel casting. Both are based in a mold. In the case of VPP process, the mold is a laser drilled polycarbonate plate, and the shape is basically the embossing of the ceramic paste. The ceramic paste is composed of powder, polymers, and solvents. So just embossing this ceramic paste against the mold to obtain the microcomponent. The main limitation of this technology is that the mold is disposable. So we just use the mold once, because the mold needs to be dissolved, so chemically dissolved, after embossing the ceramic. So due to that, as a consequence, this process has a low process scalability. So the second or another technology is called gel casting. In this case, we have a soft PDMS mold replicated from a hard master, and compared to VPP, this technique has the advantage that the mold can be reused. So we can use the mold several times to obtain this kind of things. So we just replicate the mold from a master. The master could be polymeric or metallic, and we cast the suspension inside this mold. After gelation or in-situ polymerization of the suspension, we just remove the green sand, and then we have the ceramic micro device. The limitation of this technology is that we need a master to obtain the mold. And usually the technologies used to obtain these masters are expensive technologies, so silicon-based photolithographic processes usually used in electronic industry. So another limitation or another requirement for this technology is that we need a high grain strength for the molding these microparts. And in the traditional gel casting that uses as gelation system monomers, initiators and crosslinkers, the grain strength that we obtain is in the range of 15 to 18 megapascal, which is not enough for the molding. For example, high aspect ratio microcomponents. When we try to demold these microparts, part of the piece becomes inside the mold, another part becomes so. The piece is damaged during the demolding step. So we need very high grain strength for the demolding step. So which is the main target is to avoid the use of master or masks to obtain the mold. So what we want is just to obtain the micro component directly in the mold without using the traditional approach, master approach. So for that we have two approaches or two ideas. One is the advanced ceramic shaping process that we developed. Is a new gel casting process we call the epoxy gel casting. Another one is a masterless mold fabrication, which means structuring directly the PDMS material by laser. So epoxy gel casting, as the name said, is based in epoxy resins and hardener as gelation systems, and we just mix the ceramic powder with solvent, with the eco-solvent resin, solvent and dispersant. We prepare a high concentrated and well dispersed suspension. Then we have the hardener, and we cast the micro molds to obtain the ceramic piece. After the gelation inside the mold, we can demold and then sintering. So in this case, we can obtain green strengths as high as 35 or 40 megapascal, which is enough for demolding the green piece without damage. This technology still needs, so we still master dependent of the mold fabrication, so which is the solution, as I told before, is just structuring directly with the PDMS by laser ablation. So with this we can have a more flexible design, and we can improve significantly cost and process efficiency. So with this technology we produce two products. So I have here two demonstrators for this technology. As I told, microneedles and piezoelectric pillar structures for high-frequency microtransducers. So in the case of pillar structures for microtransducers, you can see that we have the same, we have high aspect ratio, but we have the same size in the top or in the bottom. In the case of microneedles, we have different sizes in the top and in the bottom, so we have sharper micro components. We should have fine tips for easy penetration in the skin, and to increase the complexity, we should have a hole inside each micro components for the drug delivery. So the main challenge between these two micro components is in fact microneedles. So find a way to obtain these kind of things at a reasonable price is not easy. So I will talk a little bit about microneedles because maybe most of you don't know for what we need microneedles and what are microneedles, so I will tell a little bit about this. So the microneedle research started in the 1990s, and microneedles are usually an array of needles with 0.5 1 centimeter length. And the typical dimensions of each microneedles can vary. For example, the length can be from 50 to 1.5 millimeters. 1.5 millimeters is the maximum length. The width could vary between 10 and 250 micrometer, and the hole diameter between 8 and 200 micrometer. Also, the tip radius, so here this part should be less than 10 micrometers. The applications for this kind of microcomponents are drug delivery, for example, vaccination or diabetic people, but they can be used also for biochemical sensing. Which are the main advantages of this kind of microcomponents? They are minimally invasive interface with the body, but the main advantage is painless. They are painless. So, because of the small length they have, they doesn't reach the skin layer responsible for the pain sensation. So it's why this kind of things are painless for the body. So if we think, for example, that children can cry when looking to a normal needle when they want to go for vaccination, so if we use this kind of product, it would be a very revolutionary microcomponent for this kind of application, for example. So we have different kinds of microneedles: solid, coated, dissolving, or hollowed. The solid microneedles are only used for port formation. So we just put this in the skin, we remove them, and then we apply the drug. We have also coated microneedles, so we just coat the microneedle with the drug we need to put in the body, and then we put the microneedle, insert in the skin, and we remove the microneedle after the absorption of the drug. We have dissolving ones. In the case of dissolving ones, the drug is encapsulated inside the microneedle material, and everything is absorbed to the body. And then we have the hollowed microneedles for drug transfer to the body. So in terms of fabrication, these are the most difficult ones because we have a hole inside a very small thing. And the strength of the component decreases a lot when we have a hole inside this small micropart. So which are the functional requirements we need in this kind of things? Here is the skin penetration. So for that we need fine tips, we need sharper, and we need high strength. We need effective drug delivery. In this case are important the hole dimensions, and it is important to avoid hole obstruction of the microneedles. We need painless material, so the length size should not be higher than 1.5 millimeters. And we need a biofunctional base material, so at least non-toxic for the body. So the materials usually are known in the market for this kind of components are metals and polymers. Maybe most of you are asking why you never see this in the hospital, or why it's not common to see. Because they are very expensive and the price is prohibitive for certain applications now. So we need to decrease the price by improving the way how to produce these, how to fabricate these kind of things. So we have here the opportunity for ceramics. We select two materials, alumina and zirconia, to fabricate this kind of microcomponents. Since they are not toxic, they have high strength also and high hardness, and they are known from the literature that we can also fabricate, for example, prostheses for hip joints in these materials. So when we talk about colloidal shaping techniques, the key point of this technique are the suspensions, the quality of suspensions. And if we think that we need to cast very small features in a mold, the viscosity, or the rheological properties of suspensions are really important. So what we need? The main requirements is high concentrated suspensions and at the same time with the low viscosity. High concentrated because we don't need very high shrinkage, we need to avoid this to keep the shape after drying and sinking. And we need low viscous because we need to guarantee that the suspension goes to the fine parts of the micromoles. So we need easy flow of the suspension. So here we have the results. So viscosity versus shear rate. Sorry, this is Portuguese. For the three suspensions we prepared, alumina, zirconia, and mixtures of gold powders, presenting 45% of volume solids with different amounts of resin. And what you can see that all suspensions presented a shear thinning behavior, so the viscosity decreases as shear rate increases, that are characteristic of well-dispersed systems. If we look to different samples with different amounts of resin, we see that the amount of resin doesn't change significantly with viscosity, which means that we have compatibility between whole components in suspension, and the aluminum suspensions are the ones that present the lower viscosity, which should be the one most appropriate for casting the micromoles. So another important property is the gelation behavior of this kind of suspension, since we will have the hardness and suspension needs to gelify inside the mold. So here we have the storage and loss modulus versus time of aluminum and zirconia suspensions in presence of different amounts of resin. So this time before gelation is the time that we have, so the time available for casting the suspensions. And as we can see, the gelation time decreases as the amount of resin increases as expected. And if we have higher amounts of resin, we have a strong gel, so we have a harder sample after gelation. When we compare alumina and zirconia, you can see that for the same amount of resin, the gelation time is lower for zirconia than for alumina suspension. So these are according to the previous results where I showed that alumina suspension are the less viscous one. So after these results, we select alumina-based suspensions for casting the microneedles. So as I told before, another requirement is the high green strength of the samples. So here we present the green flexural strength for alumina and zirconia samples with different amounts of resin. And we can see that with 20% of resin we can reach green strength as high as 70 and 80 megapascal. However, we verified that even with 50%, we reach 30-35 megapascal of green strength, which is enough for demolding without damage the samples. So we choose this amount of resin since if we use higher amounts of organics, then we will have the deleterious effect in the final properties of the material, final chemical properties of the heat. So here are presented the first examples of the microneedles we obtained. So the first microneedles we obtained from a master. So this is the mold supplied by a company that is a partner of the project. So these are the dimensions of the microneedle. So 1.5 millimeter length, complete length, and 740 micrometer in the base. And we have the tip radius 8 micrometers. So these are general dimensions of this microneedle. And this is the replication in ceramic material. So this is the green, in green state. And here in citrus, after sintering. And we can see that we can replicate even these fine parts, so the fine tip can be easily replicated in ceramic material. So with this step, we just validate that with this technology we can produce fine tips and sharpened micro components. So the shrinkage after sintering is about 20%, which means that when we project the mold, we need to take in account of the shrinkage of the material after sintering. So after that, in the second step, we try to obtain microneedles by a masterless approach, as I told. So these are the photographs of the mold. This mold is obtained by laser ablation direct with the PDMS mold. So in this case, the microneedle has a pyramid shape, and in this case we have holes also inside. So we have different pyramid-based sizes. So here, this size is the same as this one. We have the size here. We have two hole dimensions holes. One is 150 micrometers, another one 100 micrometers. This one is almost half size of this big one. So these are top view photographs in green state. You need to take into account that this will shrink after sintering. And these are side view photographs of the microneedle. So the length of this is around 1 millimeter also. The whole size, as I said, around 100 micrometers. So this is the biggest one I showed before. This is the smallest one. As we can see here, the sharpener here is not so good as here. So here we need to improve the mold fabrication, because in the ceramic part we just replicate everything that is in the mold. So the problem here is the mold, so we need to improve the sharpener in the mold. So these are the same microneedles but sintered. So you can see here that the final hole is about 50 micrometers and the length, base length, 600 micrometers, and here 300 micrometers, so almost half. So what we achieved with these sintered alumina microneedles with these dimensions, as I said already. Okay? So the second product, as I told you before, are piezoelectric pillar structures for high-frequency microtransducers. So this component has application in ultrasound imaging systems. So this device produces sound waves that bounce off body tissues and make echoes. The transducer also receives the echoes and sends them to a computer that uses them to create a sonogram. So 1,3 piezoelectric composite, that is this part here, is the active component of this device. And it consists of an arrangement of piezoelectric ceramic pillars embedded in a polymeric matrix. These components, so this 1,3 piezoelectric composite, is the one obtained by epoxy gel casting. So for that, we prepared high concentrated and low viscous aqueous PZT powder suspensions with 45 volume% of solids. The particle size of PZT is around 0.8 micrometers. So the particle size of the powders are also important in this kind of microfabrication, because if we think that we are preparing components lower than 1 millimeter, if the particle size is very high, for example, in the tip of the microneedle, this is 8 micrometers only the tip. If you have a particle with 5 or 6 micrometer size, so just one particle fill this part of the mold. So it's very important to have as low as particle size as possible also. So here we have the total image of the array of the pillars. It's around 1.5 millimeters sided here, the same here. So it's a top view of the pillars also, and this is side view of these pillars. So the pillar height, we can have different shapes also, we can prepare different shapes, cylindrical, semicircle, or ellipsoidal shape. So the pillar height here is higher than 180 micrometers, and we have as a spectration of 5. So the distance between pillars here is also less than 10 micrometers. And we can demold these kind of things. We can casting and demold these kind of things easily without any damage. Okay? As a resume, first, so with this technology, we can produce high spectration microcomponents. We can produce sharper microcomponents with fine tips and with a hole inside. So we still have future work, we still have something to do. In the case of microneedles, as I said before, we need to increase or improve the finer tip radius. This is a challenge for the mold fabrication. We need to characterize the microneedles in terms of mechanical properties and also in terms of penetration tests to see if they can penetrate easily the skin. Usually these tests are evaluated in peak spin. And the desirable cost and output for this kind of micro device is 75 cents per replicable unit, and the yield per day about 500 units. So if we reach this, we can have a very competitive product in the market. In the case of high-frequency microtransducers, so as I said, this work is more developed in University of Vilarinho also. We are trying to obtain large area processing and random pillar distribution. This is also a mold challenge. And we want also to decrease the size between pillars, so improve or increase the geometric volume fraction of pillars. So in this case, the estimation of desirable cost and output for this kind of micro devices are between 12 and 60 euros per disposable, so per component, and the yield per day in the range of 50 to 100 units with 2 per 2 millimeters. So just acknowledge the funding of this work, and then thank you very much for your attention.
Thank you, Susana, for this very interesting talk, and now is open for discussion.
I just have a simple question. I've been following a person that is now 86 years old that needs to be checked every day because he has evidence. Okay. Moving from metals to ceramic microneedles, have you started evaluating the number of microneedles that come back after puncture the skin?
I don't understand. The number of
Ceramics
microneedles?
are known for weakness and for failing on bending. Okay. Ceramics are known for their brittleness.
For brittleness,
Okay.
yes. We didn't check
Okay.
yet the
Because I was trying to imagine how many needles after 10 years the person may keep in his skin using that technique.
That's just
Other questions?
Well, I didn't know CICECO is for needles, but I suspected. So I hope that very quickly you write towards CICECO in needles, so that perhaps we can tackle all the PhD students.
One more question?
Use size only for needles because they have more favorable, more viscosity.
Yes.
So the question is it because they have a more favorable particle size distribution? That's question number one. Question number two, are you limited to any type of material so you can use this technique for any kind of material, including traditional ceramics?
Yes. The technique can be used also in traditional ceramics. We just need to check the compatibility between resin and all the components in the suspension. So it can be used, we just need to check first if the resin is compatible or not with the material. And with this we just need to measure the logical properties and everything for preparing suspensions. Concerning the other question, just yes, the alumina has a better particle size distribution when compared with zirconia also. And there is a more broader particle size, it's why the viscosity is lower also, and it helps, so the suspension flows better when we try to cast this kind of microcomponents than zirconia. Maybe if we decrease the solids loading of zirconia suspensions, we also have very nice, very microcomponents also. But by now, at this stage of the work, yes, alumina is the one that presents or gives the best results.
Other questions?
I don't know, because in this case, my work is only for shaping the parts, not the sintering is done in University of Birmingham. But I think, yes, they have a very nice sintering properties also, yes, after sintering. The density is high. And they use lead zirconated and it has the piezoelectric material, so they use for this kind of micro components. And after that, I don't know, we can go a little bit. For a polymer, yes, for HEMSET, they use an epoxy resin. They call it epoxy resin, I don't know which kind of. Okay.
Okay, let's thank Susana again. Professor Paula is taking care of the closing session.
Hello to everybody. I've not been talking with you that much because I've been a little bit busy. But as I said yesterday, I initiated in Portuguese and I will close in English. But before ending, I will call Nuno João and Paula to attribute the prizes, the final prizes. So as you know, we have two contests. One was for the poster and the other one was for the showcase. So I will deliver this job to both of you. So please come here and you give the award. Maybe you should say who was in charge of this evaluation and who are the winners. And then I will close. Maybe you start first because you have more. So,
So we choose to give 4 honorable mentions, and the first one, if there is no order of this presentation, goes to Ricardo Santos, and the poster was the curious case of shoe-outsole discoloration. I don't know if he more famous in this category. And we give this award. Approximation to the problem that we had. Well, thank you. Another honorable mention was given to Mohamed Mawi. Highlighted the interest application. They found a very narrow market, but a very interesting market for their nanoparticles, and this was acknowledged by the jury. Thank you. Another honorable mention goes to Will Watch for the poster ceramic tiles for indoor temperature control. Of the ability of them to integrate nanofunction in a nanomaterial that is able to sense temperature, in this case, at the nanoscale level. And it goes to Majesty.
equipa de showcase, que hoje de mim, a Paula Paz e eu. Portanto, estou eu aqui, mas é de nós escolhidos, obviamente. Primeiro queria dizer que o júri foi instituído pela doutora Paula Roca, da Aveiro, pelo Marc Willinger, da James Plattner, e pelo investigador mecânico do foi investigador do CICECO e neste momento está ainda como investigador do CICECO, mas está na Alemanha. No caso do showcase, houve dois showcases que ficaram executivos. Um que está mais próximo da comercialização e um outro que tem um grande potencial de aplicação. Vou começar pelo que está mais próximo da comercialização, que é o showcase da Ana Reis, funcionalização da nanocelulose e xilana solúveis, desenvolvimento de novos produtos com origem na pasta branca de prato. Apesar de ainda estar um pouco mais longe do mercado, com o showcase do Carlos Brites, nanotermometria, um grupo de vírus orgânicos e inorgânicos funcionais do CICECO.
That have been changing all over the time. So I'm not completely sure if these are really the last figures, but we had 450 registered participants. And I think this is a big number. And it was even over what we expected and what we targeted. And I will tell you a little bit what we did before. And among these, we had 133 participants outside of CICECO, and 111 registered from companies. And this was really, really good. We didn't target so high number from the companies. As you know, we had 8 invited talks, around 134 posters. We had 28 showcases, and we had a RAM session. Here again, the number of posters was quite good for us. And also the number of showcases was really a record, because when we launched this idea, I think we were not very well understood at the beginning. So everybody was saying, this is not for me, this is not for me. But as the time moved on, I think the researchers started to understand that there is also a way of communicating science that is not only by papers and by posters. So I think this is also a very interesting number. So I think that I can say that this is really a success. So I feel good from this point of view. But I also know, and this is very clear to me, that the success has at least 2 components. And one is called an extremely hard work. So some of you know that I live currently in Austin, on the other side of the Atlantic. And one of the things I hear every morning is that massive actions give massive results. So this is one of the mentalities that the group I'm working with have. So if we work very hard, we really get good results. But I also think that this is one part. And to be honest with you, we worked very hard. But the other thing is the team. And the team that was involved was really a fantastic team. And you will understand also why. So I think that we were very well organized and everybody was working for the objectives we defined before. So I'm really pleased to have been working with all of these guys. Okay, let me share with you a little bit of what was our life for these months before, and I want to share with you and show you a little bit of what was the backstage. Because I think this needs to be shared. Okay, so once upon a time, and this was February 2014, I received a phone call from Luís Carlos saying that he would like to talk with me about Jornadas CICECO. Then later, we did a trip together to Coimbra. And by the end of that day, I received this email. So please thank Jornadas CICECO. Okay, so I thought a little bit, and at the beginning I was not very interested, to be honest, in doing this, but then finally I realized that if we could do something different, this would be an opportunity. The fact that I think that the things we do in CICECO can be shown in a different way. So this was one of the meetings I had with Luís Carlos in my office, in which I said, okay, let's do it this way. But this was March 2014. So then many things happened, and then finally we fixed the date, 15 April 2015. Finally this was. I received many emails from João Rocha saying, how is Jornadas going? How is Jornadas? And finally we find the date. But then there was a problem. And the problem was 7,000 kilometers of difference. And I was in Austin because I already contracted my life there. And the rest of the team was here. But fortunately, we have an amazing friend. And this friend made my life very difficult. At the beginning, we had 6 hours of difference. Then suddenly, we start having 5 hours of difference. So I was running to the office to be able to talk with these guys. And this was our life, okay? So almost several times per week, I was closing my office, talking with these guys. But the interesting thing is that the one girl called Sousa Paz was always in trouble because there was never a computer and we are always waiting for Ruben to be connected. So this was all my morning, 7 o'clock in the morning, 8 o'clock in the morning with these guys. So to be honest with you, I think that the board of CICECO should offer a Mac to Paula. Because it's impossible to work if you don't have the right tools. So please, João, find a Mac.
She already has a Mac.
Okay? So this was our working. Sometimes I was with Ruben and with Paula. Sometimes I was with everybody, you know, and sometimes we were alone. But we also meet here, and we work very hard as a team. So I'm very thankful to all of you, otherwise this would not be possible. But this is to say that we work very hard. But now, personally, I also have to acknowledge other people. And this is one of my back team that discussed with me many of the issues that allow me to think the way how to organize all of these questions around the nanotechnology and transfer. So these are my friends, or some of my friends all over the world, with whom I discussed how these things can be done. And to be honest with you, I'm very thankful to João and Luís Carlos when they invited me, because this work I did, it opened to me an enormous amount of doors. And I know many people now in Europe and in the US working on nanotechnology that is ready to help us. So this is only the beginning of the story. We work very hard, but the reward is also interesting. Okay? So I have to thank also to the team, the volunteers. And here I should say that in the US, being volunteer is extremely important. and I do understand this. So all of these guys worked for free, and I'm very thankful to everybody that did this. I think it's also very important to also acknowledge the back office. The back office is very, very important, okay? So these are the girls to whom we pick up the phone and ask things and things happen. Hey guys? Okay? This is the back office, so we should be thankful for the back office. Of course, I'm also, and now I'm speaking as the representative of the organizing committee. We are very thankful to all of the speakers. We are also very thankful to the jury members, and these guys helped us to do this analysis, and I think this is also important. And we are also thankful to the sponsors. Although we started working late in terms of sponsoring the meeting, there were a couple of companies that immediately responded saying, what you are doing is interesting, we should support you. And of course, I'm ending here, my job is done, and I would like to thank you all of you.
Ok, boa tarde a todos. Antes de nos despedirmos e encerrarmos as jornadas, deixem-me só dizer um pequeno apontamento, que é o seguinte: eu de facto fui incluído nesta comissão da organização, mas o que eu fiz foi basicamente desafiar a Paula a organizar estas jornadas e depois não fiz rigorosamente mais nada. Portanto, todos os créditos que foram listados devem ser endereçados à equipa que organizou as jornadas, como a Paula, e muito bem, na minha opinião, listou, mas eu não queria deixar de, em nome da direção do CICECO, agradecer publicamente à Paula por ter aceitado o repto, por ter feito uma coisa diferente, inovadora. Esta universidade, durante muitos anos, carregou a bandeira que, enfim, fazia coisas à frente das outras. Isso às vezes é bom, outras vezes não é tão bom. Neste caso, eu acho que foi uma iniciativa inovadora e que, enfim, deve-se à Paula, e eu agradeço isso, e pedia que, de facto, encerrássemos as jornadas com uma salva de palmas à organização e à Paula.